Hello, everybody. Welcome to more pre-calculus. We got our polynomial intro lesson here. I'm hoping that this is actually working. Seems like it is. So here we go. You can see right in front of you here, we're going to talk about this limit. I don't want to get too much into the algebra today, just a little short idea of what's going on. We have a polynomial function in the numerator. We have a polynomial in the denominator. This one, from your power functions chart, x to the fourth, basically takes over. It looks like a flattened out parabola. X squared is a parabola. So what does this whole overall function behave like? Well, the idea is to look at the ratio of the leading terms. And we'll talk a little bit about that as kind of like a warm-up, get your math brain flowing. And then, we'll kind of go through this lesson and get this done with relatively quickly. Again, it's the video. I'm going to try to go a little faster so that you can pause and kind of just, rewind or whatever. Instead of me just dragging it out and then having a 35-minute long video. So here's the deal. I'm going to switch over to the big mode so you can see it. There's our problem. We want to know what's going on. This function looks however it looks, but I'm not even bother graphing. I'm not going to bother doing anything with it really, except I'm going to do berserker math. And what I mean by that is I'm going to do the things that we've been telling you not to do for years. I'm going to say it is basically completely, totally okay to ignore that stuff. Why is it completely okay to ignore that stuff? Well, here's the deal. As you're going to infinity, again, this ratio of leading terms, and if you're an Arrested Development fan, Steve Rolt. Ratio of leading terms. Why is this the lead term? Well, you've talked about polynomials since like 7th grade, 8th grade maybe. The idea is that we stack them in order from largest degree to the smallest degree. Largest degree to smallest degree. So the leading term happens to be the term with the biggest exponent. Okay? So let's think about this for a sec. Why do we care? Why are we able to do bad math, all right, for x going to infinity? I'm going to ask you a couple easy questions. How many times bigger is infinity to the fourth than infinity cubed? Well, correct. If you said infinity times bigger, you would be correct. How many times bigger is infinity to the fourth than infinity squared? You would say infinity squared times bigger, and you would be correct. So basically, squiggly equal signs. Because it's not equal to, if I plugged in a number of 71, let's say, we would get an exact value if I plugged in x is equal to 71. But if I let this thing go on and on and on and on and on towards infinity, what would happen? Well, this whole big weird function, even including all the stuff that I crossed out, is basically behaving like this. The main player in the numerator is the 3x to the fourth. The boss player in the denominator is 2x squared. Now, we can simplify that because we know stuff, because we're seniors in high school. All right? And if you're sitting there saying, I'm only a junior, you're an advanced junior, so you're basically a senior. So here's the deal. Here's our scenario, 3 halves x squared. We got to think about this. What does 3 halves x squared look like? It looks like this. All right? So as x gets really, really big, what does y do? It too gets really, really big. Fake math right there, crossing out stuff. We told you couldn't do it. Turns out you still can't do it. All right? But you can use the ratio of leading terms idea. More on that to come. Just a quick little warm up, get you thinking about it. If you need to look at a graph from the original versus what I reduced it down to, please feel free to use Desmos, put them both in at the same time. See what happens as you let x get bigger and bigger and bigger. Remember, there's no way to go out to infinity on Desmos, but you can go out to like 600,000, and I'm pretty sure the point will be made. This graph will keep on getting bigger. Alrighty then. The lesson. Let's see if this works. This is my second attempt at a video. I got about 20 minutes in yesterday and everything froze. This morning, 7:30 this morning. All right, polynomial functions. That's where we're at. That's what we're going to be looking at. Just got an email from a student. Please stop emailing me because I'm not going to do my work. Oh, that's hilarious.
Are you serious?
Yeah. Oh, that's funny. Alrighty. So polynomial functions. Some are difference of power functions. We know about power functions. We've got a whole chart. If you don't have your chart out right now in front of you, the chart that we assigned a couple of weeks ago, maybe last week, I don't remember, please, dear God, get the chart out. Everything is based off of that chart. But we're going to look at only positive integer exponents. So basically, x to the first, x squared, x cubed, x to the fourth, x to the fifth, so on and so forth. Alrighty? All right, first example looks like this. Here we go. F of x equals x minus 4. All right, everybody knows what this graph looks like. Here we go. We got a y-intercept of -4. We got an x-intercept of +4. We have no asymptotes, but what I'm interested is what happens long term. Well, as x gets wicked big, so does y. As x gets wicked negative, so does y. So we have this behavior happening right here. Long-term behavior, just like those Khan Academy things that were already assigned that some of you have done and some of you have not. They are due today, by the way. So basically that's how it looks. And now, if this were a cubic, all right, it would have the exact same approach as the line, except it would just be curvier. If it were x to the fifth, it'd have the exact same approach as the line, except it'd flatten out around the origin and grow a little quicker. All right? If it was x to the seventh, same thing. X to the ninth, same thing. Are we beating a dead horse? I would think so. So that's the idea. Now, we're going to focus in on one other little detail. As we get closer and closer to 4, what's happening? All right, this goes back to Rachel B. earlier in the year when I said, why do we care about setting stuff equal to 0? Why do we care about the roots, the solutions, the x-intercepts? Well, if I solve and set this equal to 0, it's pretty easy to see that x equals 4. But here's the gist. If I approach 4 from numbers that are slightly smaller than 4, like 3.9999999, I will get back the limit being 0. However, if you actually do the calculation with this thing, I'm putting in 3.999 for x, and I'm subtracting 4, I'm actually getting a number that is extraordinarily small, but negative. If I approach 4 from numbers that are slightly bigger than 4, watch what happens. I still will get 0, all right? So the graph is going to 0, just like we've already talked about in previous days before this quarantine. But if I do the actual calculation here, what is 4.000001 minus 4? It's positive and really small. Okay? So the idea there, why am I showing you this, is that when we approach 4 and we're slightly below, we have negative numbers, and we approach 4 and we're slightly above, we have positive numbers. So at this particular root, there is sign change. We're going from a negative to a positive as we go left to right. Alrighty? If you need to, pause it, rewind it, take a look. I'm about to erase. Here we go. Back over here.